Hello everyone, this is class 2.2.2 about force undamped oscillation of vibrational dynamic series. So in this class we will discuss about the forced undamped oscillation. Compared to the previous class, which was about free undamped oscillation, in this system, which is spring mass system, we apply a force at a frequent time. Therefore, we need to derive its own equation of motion for this single degree of freedom. Therefore, of course, we are going to apply Newton's second law. If we have the mass and we put it as in a free body diagram system, we can see that this object is moving in a coordinate system. If we assume it is going to the right as a positive, what will happen in the system, right? So we have to balance the forces acting over that one, okay? And we'll check what force is acting over it. So as this mass is moving toward the positive direction, right? So as the mass is moving or forced this direction, then we can assume the force acting in the same direction of movement, and this one is the Ft, which is the applied force. And as this object moving to the right, of course there is a force or potential inside the spring by which it will try to pull it to its state of equilibrium. So therefore the force acting opposite to that will be the spring force, Fs. So Newton's second law states that the summation of all forces acting on the object will be equal to mass multiplied by acceleration. What forces it will be? So the mass multiplied acceleration will have a positive external force, Ft, and negative spring force. And the spring force is nothing but it is minus, it should be minus, okay, minus a kx. So now we have this system. We will move this part, which is the spring force, to the other side and keep the external force which apply and could move the system against the spring. So Ft will be mx double dot plus kx as it's going from this location to, from this part side of the equation to the left side. But the applied force, it will have magnitude and also direction, okay? So the magnitude will be F naught, or the amplitude of force will be F naught, and how frequent it is will be cosine omega t, right? Then we can make this equation as the following. Will be m double dot x plus kx equal to F naught cosine omega t. Remember that omega in here is nothing but, it's not the natural angular frequency of the system, but for the driving force. So this is the frequency of the driving force. The solution for this equation will have to find the steady state. So we'll find steady state solution as time goes to infinity. So the displacement will be equal to the amplitude A cosine omega t. Alright, we have x in here. So we can substitute x, this term, instead of x in there. But what about x double dot, which is the acceleration? It's nothing but the second derivative of the displacement. And the derivative will be based with respect to time. So the first, which is the velocity, which is not included in this equation, it will be the derivative or the rate of displacement, okay, and that one will be equal to the derivative of, remember that, a constant multiply a function. Okay, let's call this function f. The derivative of f will be the derivative of a for product rule multiplies p plus a multiply the derivative of p. We have the same in here, but the first term is a constant. Then the derivative of constant will be 0. Multiply this one will be 0 plus the derivative of cosine omega t multiply a. So a will last. Derivative of cosine will be minus sine. Then we'll have minus sine omega t. Then omega t. Then we have to find the derivative whatever inside the parenthesis in here. Omega t, which is t is gonna be 1, and what's remaining, which is omega, and we multiply it in here, then we'll have minus a omega sine omega t. But the purpose of this one to find the acceleration, which is the rate of velocity. So we'll have the derivative of the velocity or the second derivative of displacement. So we have in here, similarly, we'll have sine omega t, its derivative will be positive cosine omega t. Then we are left with minus a omega cosine omega t. The derivative, whatever inside, will be omega. Then we have omega multiplied by omega, have omega squared. Then now we stated how to find x double dot, which is the acceleration and the displacement. Remember that a cosine omega t is nothing but the displacement. So what we'll have, we can represent that by minus omega squared, which is the frequency of driving force multiplied by the displacement x. So we can use this one as substitution in this general equation of motion, right? All right, the next step is to do some substitution in this equation. So to substitute that, this double dot will be minus omega squared x. Then we'll have minus m omega squared x plus kx in here equal to F naught cosine omega t. Alright. So let's have a common factor as x. Then we'll have in here k minus m omega squared x. Oh, sorry, there's no x in it. We'll have k minus m omega squared x equal to F naught cosine omega t. Therefore, but x will be a cosine omega t, which is the amplitude. So what we'll have, we'll substitute x m omega squared a cosine omega t equal to F naught cosine omega t. If we divide it by cosine omega t for both sides of the equation, we will get the equation of, so we will cancel this one, and the amplitude or maximum displacement amplitude, the maximum amplitude A will be F naught over this term, which is k minus m omega squared. Alright, this is the maximum amplitude of oscillation, right? Maximum amplitude of oscillation for this force undamped oscillation, right? This is how to find the amplitude, but the solution for this equation, will be x t is equal to F naught k minus m omega squared, right? But so this one will be, the solution for this equation will be based on time, the amplitude multiplied by cosine omega t. The maximum amplitude for that, we determined it in here, and that one will be F naught over k minus m omega squared multiplied by cosine omega t. So this is the solution for the equation. All right. Let's continue. So in this equation, let's try to guess if omega approaching 0, what will happen? If omega approaching 0, which is the angular frequency of applied force, then we'll have something called static oscillation. And that one will be then the amplitude, this one, the amplitude will be equal to F naught over K. Right? What about if we what about if omega goes to infinity? From this equation, if omega is going to be infinity, then this amplitude is going to be very close to 0. Then the amplitude, therefore, going to be equal to 0. Finally, if the applied force or applied angular frequency is equal to the natural frequency of the system, then what will happen? So if that one is, if omega is approaching omega naught, we'll have a peak, and that peak is the maximum amplitude. Therefore, the maximum amplitude will be plus or minus infinity. Plus or minus infinity. Means, so if we would like to know that if we have a relationship between the amplitude, right, and the frequency ratio between the applied angular frequency to the natural frequency of the system, if the value is very close to 1, then we'll have something like negative or positive. All right? Negative or positive. At this point, it will come something like up, then down, which is maximum, then again back to normal. Okay, so we have this kind of relationship, either to go to positive infinity or to go to negative infinity. So this is when it comes to 1. When it comes to infinity, or the omega is more than omega naught, then it becomes very close to 0. And to explain that in a graph, or in graph phase, so this one, we have this graphs, okay? R is nothing but it will be the frequency ratio, and M, let me say this is resonance, right? Resonance. Just to remind you what we have studied in dynamics 2. So if omega is equal to omega naught, then we'll have resonance. Alright, so in here, if we have in the horizontal axis the frequency ratio, R, and in the vertical axis we will have the amplitude ratio, M, amplitude ratio, this is R, M, and that's M is gonna be A, which is the amplitude, what you have calculated, over the maximum amplitude, which is the F naught, which is the applied force, over the spring force or the spring stiffness K. So what do we understand from this graphs? Okay, let's look. When this one when omega very close to omega naught, so either the amplitude is going maximum infinity positive infinity or maximum negative infinity. So as omega over omega naught is increasing toward infinity, so the amplitude will become very close to zero, very close to zero here. Okay, so approaching zero. As we go infinity, it's going to be approaching zero, right? What about if it is less than 1? So less than 1. So either it will come from positive infinity and it's gonna be 1. What does it means? Means we will have the amplitude, okay, calculated amplitude over f naught over k is approaching 1. Means the amplitude actually we will have the static oscillation, right? We'll have static oscillation, means the amplitude of the system is equal to the f naught over k. Okay, then we'll have the amplitude ratio is 1. Okay, then it's going to be very close to 1. So this is, and as the amplitude is increasing, then it's going to be going very close to infinity. Right? So this graph you should understand and know how to explain if it comes in the exam. Right? Let's stop at here. Now we have this example about forced undamped oscillation. So let's read this question. A mass spring system within a packaging machine. Okay, packaging machine. So with an effective mass of 2 kilograms. So we have a packaging machine that. Alright, so let's draw the system. So we have a spring and we have a mass moving freely, and the mass is 2 kgs, 2 kilograms, and spring stiffness K will be 45 Newton per meter. Is subjected to oscillating forcing function described by Ft is equal to 10 cosine 3t. What is the steady state amplitude of resulting oscillation? Steady state amplitude A. So steady state amplitude of the resulting oscillation. So we need to find steady state amplitude. So how we can do that? The first thing, let's analyze this one. So Ft generally, let me write it in blue. Ft will be equal to the amplitude cosine omega t. Therefore, from this equation, we can get the amplitude as 10, alright? And omega will be 3 radians per second. So how can we find the steady state amplitude of the system? Right? So, no, sorry, this is not the amplitude, this is F naught, sorry. So this one will be F naught, be 10. Therefore, the amplitude, which is, this is F naught, the amplitude will be F naught over K k minus m omega squared. Alright, then it will be so this is the maximum amplitude, and that one will become f naught, which is 10 over k is given as 45 minus the mass is 2 kilogram multiply omega, which is 3 radians squared. So let me use the calculator. So this one will be 9 multiply 2 will be 45. 9 multiply 2 will be 18 minus 18. So 45 minus 18, you will get so 5 minus will be 7, will be 27. So we'll have 10 over 27. Okay. So this one will be what? Meter. We'll have it as meter. Okay. If you calculate that, 10 divided by 27, you'll get around 37.370 meter. Okay, so this is the answer of this question. Let's stop right here and see you in the next class.